Today I would like to talk about inorganic anions and their reactions. So obviously that can be a 700-hour lecture or maybe a 45-minute lecture. So let's just shoot for about 45 minutes here, or maybe an hour, split into 2 to 3 lectures. So, you know, we don't get bored. And so a lot of this is different from what I've shown you before. It's more, we're looking at structures, at minerals, at reactions, and kind of some essential basic chemistry is what this is all about. But a lot of it you are familiar with, and some of this is going to be review, so that's a good thing. But we can, and this is just one way to do it, we can divide inorganic anions into 4 different groups. The simple anions, right? So the source of these obviously are ionic solids. So anything like sodium chloride, if it's aqueous, is going to break into sodium and chloride ions. And so here we have a simple anion, chloride, oxide, cyanide. Then if these single elements are combined with oxygen, we call them the oxoanions. That's class 2, like the sulfates and the phosphates and the carbonates, etc., nitrates, nitrites. And I'll go through each of these. This is just an overview slide. And so you've had to memorize the polyatomic ions, obviously, so you're well familiar with it. But so the polymeric oxoanions are very interesting. They lead to materials like silicates. Silicates are silicon oxygen compounds. Borates are boron oxygen, and then phosphates, condensed phosphates, you know, ADP and ATP, if you've taken any kind of biology, in a sense, are those types of compounds, and we'll look at those. Those are very interesting. And then finally, the complex halide anions. So as you know, if you have highly charged larger transition metals such as aluminum, or here in this case tantalum, they are good Lewis acids, and so it is entirely possible that halides like chloride, which is a weakly coordinating anion, or fluoride is a little better than chloride, but anyway, they are Lewis bases, and so they can form these complex halide anions so it's really just a Lewis base, Lewis acid character. All right, so let's jump right into the simple anions. Like I said, any ionic aqueous solid or soluble solid is going to produce cations and anions, and so those are the simple anions. Sodium oxide, for example, if the minute it dissociates into oxide, oxide is an extremely strong base, stronger than hydroxide. It'll immediately react to form hydroxide. So relative acid base strength, right? So oxide stronger than hydroxide. Yeah, makes perfect sense. We don't really think of hydroxide as a Lewis acid, right? Or an acid, period. But if you consider hydroxide a proton donor here, right, it would have to dissociate into oxide and hydronium, and so that would mean that this conjugate base is very strong, right? Because the equilibrium is going to be way over to the left, right? Look at the K here, right? So there is essentially no equilibrium here, and so if you do have a source of oxide, it will be a very strong base. Just some general chemistry review. Metal oxides and non-metal oxides react differently with water. In general, metal oxides and water will produce bases. Of course, they have to be soluble bases, right? Like sodium oxide, for example, will produce sodium hydroxide in solution, but something like magnesium oxide, which is not very soluble, there'll be no reaction. So as long as your product is a soluble hydroxide, and calcium hydroxide itself is sparingly soluble, so that reaction will occur, but you just go back to the solubility rules. And then metal oxides will produce acids, right? So we know that if we pressurize water with carbon dioxide, we get carbonic acid, we get this equilibrium here, and so the carbonation part is of course from this pressurizing. And so the bubbles are in carbonated drinks, soft drinks, are carbon dioxide. We can do the same with dinitrogen pentoxide. And of course, if we burn any kind of fossil fuel or coal, in a power plant we get carbon dioxide, but there are also sulfur impurities, and so if you get sulfur dioxide and you combust it in a coal plant, you will actually, and then this is where acid rain comes from, right? So you've got this reaction where you get H2SO4. It's a little bit more complex than that, but for the most part, that's what causes acid rain. And so we don't really use high sulfur content coal for our power plants. And you just go to nuclear, problem solved. Acid rain. The source is sulfur dioxide from the combustion of coal or any fossil fuels that contain sulfur. And so also, you know, if you have biomass, you're going to have also some nitrogen. So there's that possibility, but there's a lot less nitrogen in these things. So just remember that. That's important. Metal oxides and non-metal oxides. Antimony, it's a metalloid. So we're looking at the metalloid oxides now in between. And in the case of this antimony oxide, we get no reaction, but it can actually react with a base, with a strong base, to form this hexahydroxy stibate complex ion, right? So we turn antimony into stibate when it's anionically charged, right? We know this already. Sodium oxide and silicon dioxide in a fusion reaction produces sodium silicate, which is actually an important material. We can grind this to a powder like this, and it can be used as a fire retardant, or, you know, textile processing and other types of materials. So that's a pretty important example of a useful compound here, right? Amphoteric oxides, meaning that they can act both as an acid or a base. So zinc oxide, for example, can act as a base and react with acid to produce water, zinc metal. So that's one example. If it reacts with a base, you get this complex, this tetrahydroxy zinc. This is obviously, it's some sort of dimer, not important. The important part here is the vocabulary here. Amphoteric can act as a base or an acid. And then the inert oxides are dinitrogen oxide, carbon monoxide. This is just 3 examples. There are several. Of course, carbon monoxide will actually react with oxygen to form carbon dioxide, but that's a slow reaction. So this, you know, we all are aware of the dangers of carbon monoxide, right? Which is the result of a combustion with insufficient oxygen, right? So don't ever cook a steak on a propane gas in a garage, right? That's a rule of thumb not to do because of the carbon monoxide. Other amphoteric oxides are the chromium oxides, and so at this point I stare into the audience and I ask, what are the IUPAC names of these compounds? And I don't really get good answers. This is my normal experience, but so I'll get something like chromium trioxide, for example. Of course, these are ionic compounds, so you need to use a Roman numeral. So this would be chromium 2 oxide. This would be chromium 3 oxide, and then this would be, oh gosh, so this would be not chromium 3 oxide, obviously. This is chromium 3 oxide here. This is chromium 6, all right? We have 3 times -2, which is -6, so this has to be chromium 6 oxide, right? So that's the proper name for these. You got to use the Roman numeral. If you Google this here, you will come up probably with chromium trioxide, and so we already know that's a valid name because chromium has an electronegativity that's rather high for a metal, right? It's not at all like sodium, which has a low electronegativity. And so it does have a covalent character. In fact, a lot of the transition metals get these prefixes when they are bound to nonmetals, and because of its high covalent character. However, if we are using the IUPAC naming scheme, then that's what we should do. We should use the Roman numeral. So that's chromium 6. Just to make sure we have, this is +2, this is +3, and this is +6, right? So they all, as I said, they are amphoteric, and so if you hydrolyze chromium 6 oxide, then you get chromic acid. If you do this with chromium 2 oxide, you get something that's unstable. This will further react. So this chromium hydroxide here will actually further react. And so what I do a lot of times on a random quiz, I review the binary naming. So here's your warning. Please review how to name binary compounds, and then I will sneak in things like C2H4, which you will name incorrectly if you're focused in on the binary naming. But when you take this quiz, you want to remember everything you know, including your 2 semesters of organic chemistry, recognize organic compounds, and that they are named differently, as well as some of the inorganic compounds that we've named. So I'll sneak a couple of those in, but for the most part, you can spend some time reviewing. Should be a pretty easy A for you. Hopefully, I keep saying easy, but it's probably hard, right? So continuing with our simple anions, there are also hydroxides, pretty important because they are part of our acid-base chemistry. All of the soluble metal hydroxides are strong bases, so essentially group 1, cesium and sodium, lithium, rubidium hydroxides are strong bases. Then there are some group 2 metal hydroxides that are sparingly soluble. Back to the solubility rules, calcium, strontium, and barium hydroxides have some solubility, and then everything else like magnesium hydroxide is not, so those are obviously not strong bases. There is aluminum hydroxide, which is actually amphoteric, and if you think about it, it's because the aluminum to oxygen bond is highly covalent. There's an electronegativity difference of 1.83, so that aluminum is hanging on to that oxygen and it's not going to produce discrete hydroxide ions. However, you can add an acid to that to rip off the water or the hydroxide from the aluminum and get discrete aluminum ions here. But by the same token, you can also add a base to it, and so obviously this is Lewis acidic at the metal center, and so this lone pair is going to attach there to the aluminum and not rip off the the hydrogen from this hydroxide. So the chemistry there is a little bit different. It's similar to boric acid. So boric acid is also different from something like sulfuric acid, for example, and we would write, we don't write boric acid in that fashion either, right? We don't write H3BO3. That's, boric acid. You might see that written like this, but it doesn't do it justice because we don't have, these hydrogens actually do not dissociate to produce hydronium ions. It's actually a little bit different process, which I'll show you in a second here. But just back to this one, we have the first, of course, HSO4. This is weak. The first dissociation is strong, and then this produces a conjugate base, and so the second dissociation is weak. But this indicates that the hydrogen comes off of the oxygen here because of the polarization towards the center, which in this case is the sulfur. That's actually similar to what's happening here, if it does. Okay, so boric acid, what it does, it's actually, boron, we always say it's electron deficient. It's okay to have 6 electrons. I told you no, that's not true. It's in reality, it's going to find its electrons one way or another, and this is true here too. So what happens is this has an empty p orbital, and a water will come in and attach, form a Lewis base, Lewis acid type interaction, and then what happens is it's this hydrogen that comes off. So that makes it drastically different from what we expect, and that's why also the formula is not written in that fashion. So alkoxides are analogous to hydroxides. All we're doing is we're replacing the hydrogen with an alkyl group. So those are the alkoxides. Same formula, same structure. However, in the example of titanium, we get these interesting networks of titanium alkoxide clusters, And if you do an electron count for something like TiO, tetra alkoxide, you end up with 4 for titanium, 4 for the 3 ligands or 4 ligands, and then if you're lucky you can have maybe some more pi electron donors from the oxygens, but either way you're going to end up with a highly electron deficient transition metal center, and we know it wants 18 electrons, so it can form these interesting coordination polymers, either these chains, or it makes these tetrameric structures here where we have tons of electrons that are being shared here by bridges, and that's how titanium ends up with its 18 electrons, hopefully. And this is just to show you that these building blocks are octahedral. You've got this titanium alkoxide centers that are fused like this and build these networks, and so there's different kinds of compounds there. This will be on the exam. You have to reproduce this structure for every single one of them. I'm going to ask you for like G. What's the structure of G? And you better remember that. All right, carbonates. All right, carbonates. We have limestone, calcium carbonate. We know we use that in our gardens for acidic soil. We can make it basic, right? The carbonate, and of course carbonates are not soluble, but if acid is present in the soil, then we get a slow decomposition of calcium carbonate. And this is also where our hard water comes from, right? Calcium and magnesium are the 2 ions that make water hard. And so magnesium, we refer to calcium carbonate and magnesium carbonate roughly as limestone, but it's really the calcium that's limestone. The magnesium carbonate is called dolomite. If you want to be picky, not a big deal. They both will react. And so acid rain is bad because acid rain will corrode some of the carbonate limestone structures and deplete it. And so why in the heck do I have a popsicle here? Well, dolomite, that name is associated with a mountain range in Italy called Dolomiti, and so I grew up in Germany where we had this ice cream called Dolomiti, and so I guess it's supposed to be the mountain, but I just have it here for the name. It's related to that magnesium carbonate, so I am assuming, never Googled that or asked ChatGPT to answer that. Probably should, if the dolomites are actually contain magnesium carbonate rather than calcium carbonate. I'm assuming that's true. So anyway, it's not going to be on the quiz, so nothing to worry about it, right? Okay, so finishing. Oh, we're talking about. Okay, I'm transition here, right? So we're talking about the oxoanions now, the carbonates and you know, sulfates and nitrates, and also. These are insoluble, and so it's only group 1. So again, it's the lithium carbonates and sodium carbonates that are soluble, and then ammonium. So this may be new. It's not part of the usual. Of course, thallium is highly toxic. So anyway, if you add a hydrogen to any of these anions, you call it. The naming goes to hydrogen carbonate, and the same is true for sulfate. Of course, you know this is part of baking soda, and the reaction of acid with that produces carbon dioxide, which helps us with our rise to cake and whatnot, right? Carbonates can be ligands, they can be bridging or chelating. There's a number of interesting copper compounds that we use to make in the lab. Also, here's the reaction of carbonate as a base with water to form hydrogen carbonate, and then this can also further react to make carbonic acid, as we know already. So those are the carbonates. We have oxalates. That's oxalic acid that has been deprotonated twice. Oxalic acid is a good chelator. It is present in some foods like rhubarb and spinach, and I think you want to be careful with the amount you eat because it can chelate some essential minerals like calcium. And but here we have just as a reminder, this is C2 symmetric, therefore it's a chiral, the propeller ligand, right? Chelating ligands, we drew isomers and whatnot. So we can thermally decompose oxalates into carbonates and then further into oxides. And there's a really cool lab that we used to do. We used to make a number of calcium magnesium barium oxalates. We would use to make these compounds, and then use a TGA, thermal gravimetric analyzer, to decompose it. Essentially, it's just a little bit, a tiny little furnace with an opening, and then there's a little pan on a platinum wire. You can put a little bit of your compound. The furnace will then lower over the compound, and then the temperature will, you can actually measure percent mass, or just mass in general, and then temperature, and you'll see this at 300 degrees it'll decompose to carbonate, and then you can actually go in and calculate the purity of that. So really cool lab. Carboxylates, so you replace one of the oxygens with an R group, you get the acetic acid, for example. Vinegar, you deprotonate that, becomes a carboxylate, and so they can also be chelating and bridging ligands. So that's another one of those oxo-anions. Then we have nitrate and nitrites. Again, same bonding modes. Don't want to really elaborate on that too much. Be aware of the name. Know the difference between NO3 and NO2. That goes back to Gen Chem. We know that nitrite can be a ambidentate ligand. It can either coordinate through nitrogen or through oxygen. These namings are incorrect at this point. Those are old namings. Never fixed the slide. Shame on me. Let me start with the phosphates, because the phosphates are going to get us started into the oxo-anions that are polymeric. They lead to some very interesting structures. I'll show you some cool pictures. And anyway, this is enough for an introduction.